Hi, this is week 33 of AP Physics, and we're covering the last part of Unit 9, which is DC circuits. For our lesson, we're going to go ahead and be looking at Kirchhoff's rules. For our lesson objectives, students will learn how to use Kirchhoff's rules to solve for the current in a circuit. Let's go ahead and get started.
Let's begin our lesson by discussing Kirchhoff's rules. You apply Kirchhoff's rules when you have a more complex circuit. So this, we're going to go ahead and break it down to different parts of the circuit into loops, and that's going to go ahead and allow us to break it down piece by piece, and then using substitution, we can go ahead and figure out for the potential difference or current within a particular circuit. So the first rule I want to go ahead and talk about is the junction rule. And the slide states that the sum of the currents entering any junction must equal the sum of the currents leaving that junction. That is the junction rule. Next, we're going to go ahead and talk about the loop rule. The sum of the potential difference across all the elements around any closed circuit loop must be zero. That's the loop rule. Next, how to apply Kirchhoff's rules to a circuit. Number one, assign and label the symbols to known and unknown quantities. For example, on the right hand side of the slide, you can go ahead and see that we have A going to B. So we have potential difference equal to negative IR. Here, negative because the resistance is working against the current. For the second diagram, we have the current going with the resistance. So we have potential difference equal to positive IR. Now, if the current is going to the right, we're going to label that as positive. But if the current is going to the left, we're going to label that as negative, as you see right here. So number one, again, assign label everything that is known and unknown. Number two, assign the direction, so as with positives and negatives for each part of the circuit. Number three, apply the junction rule to any junction within the circuit. Number four, apply Kirchhoff's loop rule to all loops. And finally, number five, you're going to use a lot of substitution to go ahead and figure out the unknown quantities. All right, now let's go ahead and take a look at example 8 and apply Kirchhoff's rules.
Let's go ahead and take a look at example 8. Here we ask to find the current for I, 1, 2, and 3 in the circuit using Kirchhoff's rules. So let's take a look at this circuit. We got a resistor here, and we have two more here in parallel. So we're going to call this one 1, that one 2, and that one 3. And we're connected to a battery that has a potential difference of 6 volts. So now we're going to go ahead and begin with the junction rule. Notice that here current 1 is going to go ahead and split into 2 and 3. So we're going to make the following claim. We're going to say, according to the junction rule, the current 1 is equal to current 2 plus current 3. They equal each other. Next, let's go ahead and take a look at this part. We have one loop here, one loop there. So we're going to begin with this loop for the loop rule. All right, so the potential difference of the battery, so we're going to label potential difference of the battery plus, here's our first resistor, the potential difference of our first resistor, so when I label that, that is for 4 ohms, plus, let's continue our loop, our third resistor, so the potential difference for our third resistor, which is the one with the 9 ohms, all of them equal to 0. All right, so that's our next formula we're going to go ahead and use. We're going to flesh this out though a little bit more, because we know that potential difference I times R, so we're going to go ahead and put that. And I wanted to go ahead and also point out the fact that the R here and here, notice, is going against us because it's providing resistance. So those are going to be negative here and negative there. So when we plug in this formula here and there, they'll be negative again because they're going against the arrow. All right, so potential difference is going to be for the battery 6 volts minus. All right, so this is our first resistor. I'm going to go ahead and put negative IR, so that I is for current 1, and the R, we know what it is, 4 ohms. All right, and for the second one, also negative. All right, so potential difference IR, but we're talking about this one, right, because we're going in the circuit here. So it's going to be I3 times 9 ohms. And all of this equals 0. All right, so that's our next formula. We can go ahead and modify a little bit, and to make it more simple for our numbers, we're going to drop the symbols for ohms a little bit, and let's go ahead and simplify it. I'm going to write it as such. 6 is equal to I times 4 plus 9 times I3. All right, so that's the same formula again. I left out the symbols and I move the two resistors over to the other side of the equal sign. So now that was our next formula. All right, so we have this one. We have this one. Now we need to make one more claim about the loop on top. Then we're going to go ahead and substitute them into each other and solve. All right, so for this one, we're going to start right here at the junction and go around. All right, so for this one, it's going to go ahead and be the first resistor. Notice that it's the direction of the arrow is going to the right, so the resistance to the left. So we're going to say that the potential difference for our first resistor, so we're going to go ahead and label that one as 5 ohms, plus for the second resistor down here, potential difference for the 9 ohm resistor, all right, those guys equal to 0. All right, now again, let's flush it out a little bit. Let's put the I and the R for these guys. All right, so for the first one, it's going to be, notice how the resistor is going against the direction of the arrow, so that's going to be negative. So I'm going to put negative. There's going to be I2, because that is current 2. All right, it's going to go ahead and be multiplied times the R, which is 5 ohms. And that's going to be positive, because notice now the resistor is going against the current, but here our arrow also is going in the same direction, so that's positive. It's going to be I3 multiplied times 9 ohm, that equals 0. All right, so now we can flush this one out a little bit more. Again, simplify, we're going to drop the symbols for omega. Just we want to simplify it a little bit so it's a little bit easier to go ahead and substitute. And let's go ahead and do that. So this is going to be negative 5 I2 plus 9 I3 equals 0. We can go ahead and make it even a little more simplified. Move over this to one side. I3 is equal to 5 I2. All right, and let's simplify it even further. We're going to go ahead and divide both sides by 5. We just want to go ahead and really simplify it. So 9 divided by 5 gives us 1.8. So we have 1.8 E3 is equal to I2. All right, so that right there, that's going to be coming very helpful. All right, so now let's go ahead and plug in these values into our formulas. We can go ahead and plug it in here or there. Let's go ahead and begin at the very top. Here I2 equals that right here. So we're going to go ahead and make the following claim. Again, we're substituting this here. So it will look like this. I1, it's equal to I2, which we're going to substitute it for 1.8 times I3 plus I3. All right, so therefore we can say I1 is equal to 1.8 plus 1, 2.8 I3. All right, so now that we have this value, we can go ahead and substitute it into this formula. And now we can go ahead and figure out what is I3. So we're going to go ahead and substitute that right there. So it'll look like this. 6 is equal to 4 multiplied times I1, and I1 is 2.8 I3 plus 9 I3. All right, so now I'm going to go ahead and multiply both of these. So that's going to be 2.8 times 4 gives me 11.2. So 6 equals 11.2 I3 plus 9 I3. I'm going to go ahead and add both of those together. So that gives me 20.2. 6 is equal to 20.2 I3. And next I'm going to go ahead and divide, and I ran out of space here on the board, but I'm going to go ahead and divide both sides by 20.2, and that's going to go ahead and give me 6 divided by 20.2. Let's round it off to 0.3. So therefore, I3 equals 0.3 amps. All right, so we got our first current. I3 equals 0.3 amps. All right, now that we have that, we can go ahead and plug it in other places to go ahead and solve for our values. All right, so I don't need the diagram anymore. Maybe we can erase it, but instead I'll just erase this part right here. All right, so I know what I3 is. So if I know what I3 is, can I figure out what I2 is? Sure, using this formula. So I'm going to go ahead and substitute I3, which is 0.3 amps here. So it is 1.8 times 0.3 amps is equal to I2. So therefore I2 is equal to 0.3 times 1.8 gives me 0.54 amps. And there we have it. So now we have I3 and I2. Finally, now we have 2 and 3. We can figure out what is I1. And I1 is I2 plus I3. So it's going to be I2, which we just got 0.54 amps, plus I3, which is 0.3 amps. Put them together, I1 is equal to 0.54 plus 0.3, 0.84. Alright, and that is our current. So now we have all three currents. The first current is 0.84 amperes, the second current was 0.54, and the third current was 0.3 amperes. Now, that is example 8. In problem 29, we're asked the following question. How would the answer change if the indicated directions of the currents were all reversed? So if we were to go ahead and draw our arrows or the currents in a different direction, well, all the answers numerically would be the same. So they have the same magnitude. It's just it would have a negative in front of all of the answers. That is problem number 29. Now in problem 30, we're asked the following. Suppose that the 6-volt battery is replaced by a battery of unknown EMF. So now our 6-volt battery is now gone. And the ammeter measures a current for I1 equals 1.5 amperes. Find the two other currents, so 2 and 3. Alright, and we're going to go ahead and solve for this using Kirchhoff's law as well. So let's go ahead and get to work on this one. So given to us is the following. We know that I1 is equal to 1.5 amperes. Alright, and now we can go ahead and solve for the battery, which we don't know what it is, by the way. It's missing. So let's make the following claim using the junction rule. We know that I1 is equal to I2 plus I3. Alright, so we can also, again, follow Kirchhoff's rules, and we're going to go ahead and start with the potential difference of the battery. And we're going to go ahead and add, that's a potential difference of our first resistor, so that'll be plus the potential difference of the resistor with 4 ohms, plus the potential difference for the resistor with 9 ohms, and all of that equals 0. Alright, so that's a loop rule. Next, we're going to do the same for this loop right here. But before we do that, let's go ahead and flesh this one out a little bit. We don't know what this is, so we're just going to leave it as so. But we do know that for the potential difference is equal to I times R. And this resistance is going against the flow of our arrow. So we're going to actually put negative I. So that's going to go ahead and be, for the first one, it's going to be I1 times the 4 ohms. And for this one's going to be negative I3, which we do not have, multiplied times the 9 ohms, and that equals 0. Alright, so we can flesh this one out slightly, leave out the delta V here. For the battery, the potential difference is going to be 4 times I1. It's equal minus, actually becomes positive because we move it to the other side. It's going to be 9I3. Alright, so there's our formula. We can again flush it out a little bit more because we do know what I1 is. It is 1.5 amperes. So substitute 1.5 amperes right here. So 1.5 times 4 is going to go ahead and give us 6. So delta V for the battery is going to be 6 plus 9I3. Alright, so there is one of our formulas. Here is the other. Alright. Now we can go ahead and keep on working and on the second loop. Alright, for the second loop, we got 2 resistors and the current's going to the right here. And on our loop, we're going to loop it around here. So we're going to say the following. It's going to be the potential difference of the resistor with the 5 ohms plus the potential difference of the resistor with the 9 ohms is equal to 0. Alright, now this first one's going to have a negative value because the resistance going against the direction of the arrow. So we're going to say it's going to be negative I, which is I2 times the 5 ohms This is going to be plus because the resistance going to the left and the arrow here is going to the left since we're looping around clockwise. So that's going to go ahead and be I3 multiplied times 9 ohm equals 0. All right, again, we're going to flesh this out a little bit more. We're going to put for this one negative 5 times I2 plus 9 times I3 equals 0. Move over the 5. So it's going to go ahead and be 9I3. It's equal to 5I2. I'm going to divide both sides by 5. So it is 1.8I3. It's equal to I2. All right, so there's the formula that we need. I'm going to go ahead and just put them all together here so we can clear up some space. Potential difference of the battery is equal to 6 plus 9I3. And also, it's going to go ahead and be 1.8 I3 is equal to I2. All right, so those are our formulas that we've got. So now we can go ahead and start solving for the currents for I2 and I3. All right, so what I'm going to go ahead and do is I'm going to get I2 substituted here, I3. So now, again, this is going to be substituted here. So I'm left with this. I1 is equal to I2, which we're going to substitute 1.8 I3 plus I3. So now I'm going to go ahead and add both of those together. So I1 is equal to 2.8 I3. And I know what I1 is. It is 1.5 equals 2.8 I3. So I'm going to go ahead and divide both sides by 2.8. So it's going to be 1.5 divided by 2.8. So it gives me we're going to round it off to 0.54 amps. That is I3. All right, so now, lastly, I can go ahead and solve for I2. Now that I have that, I have I3. So let's use this formula. It looks a little bit easier. So it'll be 1.8 I3 equals I2. I'm going to go ahead and substitute 1.8 0.54 amps equals I2. So it's going to be 0.54 times 1.8 gives me 0.97. We're going to round it off to 97 amps. And that is I2. All right, let's verify. 0.97 plus 0.54 gives us about 1.5. There we go. So there's our answer for the current for I1, I2, and I3. And if you're interested in knowing what was the potential difference of the battery, we can go ahead and use this formula right here to go ahead and solve for that. I3 was 0.54 times 9 plus 6. So it was roughly a little less than 11 volts. That was the potential energy of the battery. They didn't ask for that, but just a little bit extra. All right, that takes care of problem number 30. In example 9, we're asked to solve for the current for I1, I2, and I3 in this circuit. Now let's take a look at the circuit. It's got two batteries, 10 volt and a 14 volt battery, and three resistors with 2 ohms, 6 ohms, and 4 ohms as well. Alright, so let's go ahead and begin by looking at the junction rule here between I1 and I2. Notice that they come together to give you the formula for, or combine to give you the current for I3. So now we're going to go ahead and put them together. So we're going to say I3 is equal to I1 plus I2. Alright, so that's going to be our first statement, our first formula that we're going to use for this problem. Next, we're going to go ahead and use the loop rule to go ahead and figure out this bottom rule, the bottom loop. Alright, so we're going to begin right here at the battery. So we have the potential energy of the battery, and that's going to be plus the potential energy for this resistor, which has 6 ohms, plus the potential energy as we loop around to this resistor, which has 2 ohms. And the loop rule says that all of them put together, all the potential energies put together is 0. Alright, now let's go ahead and flush these guys out a little bit, start plugging in values for them. For example, for the potential energy of the battery, we know that is 10 volts. Now, for this first resistor here, the 6 ohm resistor, the potential difference is current multiplied times resistance. All right, so it is current. It is I1, the current going through this resistor. And notice that we're looping around this way, but the resistance is the other way. So we're going to say it is negative. And that's going to be I1 multiplied times the resistance, 6 ohms. And as we loop around here, now it's I3 looping around the bottom. Same thing, whereas the current is going one way, but the resistance going the other. So it's going to be negative I3 multiplied times 2 ohms. And all of it put together is 0. So here we have this formula. Let's go ahead and flush it out a little bit more. So I'm going to go ahead and drop the volts and the ohm symbols and try to make it more like a formula like this. All right, so we're going to say 10 minus 6 times I1 minus 2 times I3 equals 0. And we can move these ones over here. And just to flush it out a little bit more, we're going to have 6I1 plus 2I3. And notice that we changed the symbol since we moved them to the other side of the equal sign. And could we simplify this a little bit further? Sure, we could divide all of these by 2. So we have 5 equals 3I1 plus I3. And that will be our second formula, which we're going to go ahead and put it here. So 5 equals 3I1 plus I3. All right, next, let's go ahead and work on the top loop. All right, I'm going to go ahead and give myself some space here. Now for the top loop, it'll look like this. We're going to go ahead and begin here at this battery. And notice that we're starting on the negative side. So we're going to go ahead and put, that'll be negative potential difference for the first battery. So I'm going to put battery 1, label this one. That's going to be battery 2. All right, and as we go around here in this direction, that's going to go ahead and be plus the potential difference for the 4 ohm resistor. All right, and we come around this, around the top, there's our battery again, but we're coming from left to right. So it's going to be negative potential energy for battery number 2, that's this one. And then as we come around here, we're going to loop around, and here's current 1, but notice that we're going against the current, so with the resistance, so it's going to be a positive delta V. That's going to go ahead and be for the 6 ohm resistor, and all of that according to the loop rule, it is 0. All right, so let's go ahead and double check, and this one should be negative because we're going this way against the current's going against the resistance going against the current, so that's why we have a negative there. All right, so now let's go ahead and plug in the values for them, and so for this one's going to be negative 10 volts minus potential difference is current times resistance. So the current here for the top loop is I2. So I2 multiplied times 4 ohms. All right, minus the 14 volts plus I1 multiplied times the 6 ohms. That equals 0. All right, now we can go ahead and again drop all the volts and the ohms and go ahead and make it more like a formula. So it'll look like this. Negative 10 minus 4I2 minus 14 plus 6I1 equals 0. Let's go ahead and combine some like terms. So negative 10 and negative 14 gives you negative 24. And that's going to go ahead and be, let's see, 4I2 plus 6I1 equals 0. All right, now let's go ahead and move these guys over to the other side, so that way we can go ahead and let's get rid of the negative. So it's going to be the negative 24 and the negative 4I2 move it to the other side. So we end up with this 6I1 equals 4I2 plus 24. All right, so there's our formula. We can simplify it further, divide everything by 4. So let's go ahead and do that. So that way we can simplify it further. So 6 divided by 4 is 1.5 I1. This is going to be just I2. And over here, 24 divided by 4 is going to go ahead and give us 6. All right, so this is our third formula. I'm going to go ahead and write it down here. And there we have it. All right, so we got 3 equations. This one was for the junction rule. This one was for the bottom loop. This is for the top loop. Now we can go ahead and begin to substitute these formulas together so we can go ahead and come up with the current for I1, I2, and I3. All right, so let's go ahead and do that. Now, let's go ahead and begin by a quick substitution. I3 here, we're going to substitute these two values here. So now we start out with this 5 equals 3I1 plus I3. Now we're going to say, well, I3 is equal to I1 plus I2. So we're going to substitute them here. So it look like this. I1 plus I1 plus I2 after we substitute here this top formula there. All right, let's go ahead and combine some like terms, and we can go ahead and put both of these together. So it'll look like this. 5 equals 4I1 plus I2. And let's isolate the I2, move the 4I1 over to the other side, so we'll end up with this. 5 minus 4I1 equals I2. All right, great. So this formula, we're going to go ahead and use it. And how can we use it? Well, you see this formula right here. It has both I1 and I2. Both of them have the same thing. So now what we could do is we can go ahead and substitute this into this formula right here, and then solve for I1. All right, so let's go ahead and do that. So I'm going to get this formula, 1.5 I1. It's equal to I2 plus 6. All right, so I'm going to substitute all of this here, right there. So it'll end up looking like this. 1.5 I1 equals 5 4I1 plus 6. All right, let's go ahead and start combining like terms. So I'm going to go ahead and add the 5 and the 6, put them together. That ends up giving us an 11. And on the other side, I'm going to move the negative 4I1 to the other side. So we're going to add plus 4 on both sides. So we end up with 5.5 I1. And then our last step, we just go ahead and divide both of them by 5.5. So I1 equals 2 amps. So there we go. We got our first current. I1 is 2 amps. All right, sweet. So now that we have that, we can go ahead and use it in other formulas to solve for I2. For example, this formula right here lends itself perfectly since we know the value of I1 is 2 amps. So let's go ahead and do that. So I'm going to rewrite the formula here. But for I1, I know it's 2 amps. So I'm going to go ahead and put a 2 equals I2. All right, so now we have 4 times 2. That's going to go ahead and give us an 8. All right, and then subtract, so we end up with negative 3 amps. That is the value of I2. And there we have it. So we got I1 and I2. Great. And yeah, it has a negative 3 amps value. That means it's going in the opposite direction. Now, the next part, let's go ahead and solve for the missing. We got 1 and 2. So now we can go ahead and get 3 according to this formula. So I3 is equal to I1, which is 2 amps, plus I2, which is negative 3 amps. So therefore our answer for that one is going to go ahead and be negative 1 amp. And that is the answer for I3. All right, so we have I1, I2, and I3. Those are the currents. 2 amps, negative 3 amps, and negative 1 amps respectively. All right, that takes care of example 9. In problem 31, we're asked the following question. Is it possible for the current in a battery to be directed from the positive terminal towards the negative terminal? Yeah, that is possible. It happens every time you plug in a rechargeable battery. It's going to go ahead and that scenario will take place. Next, let's go ahead and take a look at problem number 32. In this problem, it asks the following. It says, find the 3 currents in the circuit. And it says, hint, the direction of one of the currents is deliberately chosen wrongly. All right, so here is our circuit. I have top half, bottom half. It's got 2 5-volt batteries and 3 resistors with 1 ohm, and 2 ohms resistors. Here are currents to 1, I2 going to I1 and I3. And all right, so if you notice they're diverting. All right, so one of them is in the wrong direction. So we're going to make believe that it is I1. Though you can choose really I3 to also be in the wrong direction. All right, but we're going to go with I1 as being the wrong direction, so point it as going up. So therefore, in the junction rule, I1 plus I2 will give you I3. So we're going to say I1 plus I2 is equal to I3. But we're going to put negative for the I1 since it is pointing downwards. So keep that in mind. That will be a negative. All right, so that is our first statement as far as solving this. Next, let's go ahead and solve for the bottom loop. In the bottom loop, we begin with the battery. It's going to loop around to this resistor, that resistor, and come back around. In this part, we'll use I1, but for this top part, we're going to use I2. All right, so we begin here with battery. So the potential energy for a battery, so we're going to call this one battery 1, that one battery 2. So battery 1, and then we come across this resistor plus the potential energy of the resistor with the 1 ohm, plus, coming around here, the potential energy for the resistor, also 1 ohm. And according to the loop rule, as we come around, we've got one more battery, but now we're going in this direction, so it's going to be negative for battery number 2, and all of it is a 0. All right, so that's what we got. Now let's flush this out a little bit, plug in the values. For the first battery, it's 5 volts, and then that's going to be plus. Now notice that we're going this direction away from the current, so current's going this way, so we're going with the resistance, so it's going to go ahead and be the current 1 positive, because we're going with the resistance, our arrow for our loop's going with the resistance, positive, and then 1 ohm. And for this next one, we're going also against the current again, so we're going with the resistance. All right, so that's also going to be positive, and that's going to be I2 times 1 ohm, and then this one is going to be negative 5 volts, and that equals 0. All right, so we're going to try to make this one into an equation like this one, so we're going to drop the volts and the ohms. All right, and let's go ahead and do that. So we're going to write 5, and then plus 1, the 1 times I1, so it's going to be just positive I1, and there 1 times I2 is positive I2, minus 5 equals 0. Let's go ahead and collect some like terms. So 5 plus 5 minus 5, that's going to cancel out. So we're just left with this. And we can go ahead and move it over. So let's see, we're going to have I1. Let's go ahead and move over the I1. Negative I1. All right, so there's our second statement, and that's for the bottom loop. All right, so I'm going to go ahead and write it right here. I2 equals I1 negative. All right, so let's go ahead and talk about now the top loop. In the top loop, let's see what we've got. We are going to go ahead and start it here from the battery. So it's going to be the potential energy of the battery, and that's battery 2, moving through this resistor. Though, notice that we're going in that direction with the current, so therefore it's going to be negative for the potential energy for the 1 ohm resistor. And then as we go through here, again, we're going this direction with the current. All right, so therefore the resistance is going to be opposite. That is for the 2 ohm resistor. And completed over here, so 0. All right, so now we go ahead and start plugging in the values. So this is a 5 volt battery. Minus, for this one's going to be I2 multiplied times the 1 ohm. It's going to be I3 multiplied times 2 ohms, and all equals 0. All right, let's write it more like a formula. And it's going to be 5 minus I2, because 1 times I2 is just I2, minus 2I3 equals 0. All right, so at this point, let's see. Let's go ahead and isolate the I2. Maybe you should isolate the I3. Either one is fine. All right, let's isolate I3. So it's going to go ahead and look like this. So it's going to be 2I3, and that is negative, is equal to, let's move this one over and this one over, I2 minus 5. All right, so that's what we got so far. We can also move over the negative. So it'll be negative I2 plus 5. And there's our third formula. All right, so we got our 3 formulas there. Now we can go ahead and start substituting into each other and solving this problem. All right, so where should we begin? Well, we can go ahead and do a couple of substitutions. All right, so for example, we can go ahead and substitute can go ahead and substitute the I3 here. Alright, so let's substitute this top one with this bottom one, and let's see what we get. So we're going to go ahead and end up with this formula. And now for the I3, we're going to go ahead and substitute this section in here. Alright, so this is our first substitution. We're going to go ahead and distribute the 2. So we have the following. Now let's go ahead and combine some like terms. So now we're going to have this negative I2 and this I2. We can go ahead and put them together. So we end up with the following: 2I1 plus 3I2 is equal to 5. Alright, so that's the 1 right here. Alright, now we can keep going a little bit further as far as our substitution and do another substitution. For example, I know that I1 is equal to I2. Alright, so therefore I can go ahead and substitute here and solve for that. Now notice that it's negative I1 is equal to I2, so that will be 2I2 plus 3I2 is equal to 5. Alright, so now add combine like terms. So it's going to be 5I2 equals 5, and now we can go ahead and divide by 5. So therefore I2 equals 1 ampere. And there we have it. Alright, so we got our first current. I2 equals 1 ampere. Now we have that, we can also go ahead and figure out for what is I1. I1 is negative over what I2 is, so therefore that is negative 1 ampere. Alright, so we got 2 answers, and therefore now we can go ahead and plug them in here and solve for I3. So it is negative, so for I3, it is negative I1 plus I2, so that's negative 1 plus I2 is 1. Alright, put it all together, negative and negatives are positive, so the answer is 2 amperes, and that is I3. Squeeze it here at the bottom, 2 amperes, and that is problem number 32. This brings us to the end of our lesson for week 33 in AP Physics. Thank you so much for watching.